Hello everyone. Today I'm going to explain how you can calculate discrete time convolution with some examples, and we are also going to see properties of a convolution. Before I start to show you how to graphically perform the convolution of discrete time signals, I would like you to pause this video and answer this question. So the question is, considering UK, which is the unit step signal as depicted below, which option correctly shows u of n minus k for n equals to 3? All right, so let's take a look. I have the signal u of k and I want to build u of minus k plus 3 or u of 3 minus k. So I'm going to name this new signal g of k, which is equal to u of 3 minus k, or equivalently I can write it as u of negative k plus 3. So I'm going to build a new signal and I'm going to name it f of k, which is going to be equal to u of negative k. Now I need to shift this f of k to get g of k. So g of k is going to be equal to f of k minus n. So if you replace k minus n in here, you're going to get u of minus k plus n, which is what you were looking for n equals to 3. All right, so let's take a look at this process and perform the process. So I first built the signal f of k, which was the flipped version of u of k. So I have this as my f of k. I'm plotting f of k as a function of k, and this is going to be equal to u of negative k, the flipped version of u of k, 0, negative 1, negative 2, so on and so forth. All right, and then I want to shift f of k by n points to the right, and that's going to give me the signal that I'm looking for, which is g of k. So I'm plotting g of k now, which is f of k minus n. This is g of k, the same signal that I was asked to plot. So f of k minus n is the shifted version of f of k by n points to the right. So n is equal to 3 here, so I'm going to shift it by 3 points to the right. This goes forever, and this is 3, 2, 1, 0, negative 1, and so on and so forth. So this is my signal for n equal to 3. I have this one as n equal to 3. So this is my g of k. All right, so this answer is correct. Answer A is the correct answer. So to be able to build u of n minus k, which is a function of k, I flipped u of k and then shifted the signal by n point to the right. All right, so we are ready to do the convolution now. To compute the discrete time convolution, there are 3 basic steps that you need to follow. Step 1, you need to flip the signal. Step 2, you need to shift it. Step 3, you need to multiply and add. Let's see how this works. So I have 2 signals, x of n and h of n in here, and I want to find the convolution of x and h, and I'm going to name it y of n. So y of n is x of n convolved with h of n. I have the convolution equation. It's provided in here. Let's see how we can do this. In this example, we are going to find y of n point by point for different values of n. All right, let's start with n equal to 0 and find y of 0. Y of 0 is based on the equation that I have. If I have y of n, I can find y of 0. I'm going to replace n with 0 whenever I see n in the equation of y of n. All right, y of 0 is sigma x of k. I don't have any n in here, so I'm going to write x of k. H of, instead of n minus k, I'm going to write h of 0 minus k. So the summation is going to look like x of k multiplied by h of negative k, and I need to run this sum for all k values, from negative infinity to plus infinity. These two are discrete time signals, so k can only take integer values. All right, if I want to do this process graphically, I can plot x of k, then plot h of k, and using that plot, flip the signal h of k and plot h of negative k. Then I need to shift h of negative k by 0 point because I'm looking for h of 0 minus k. So for n equal to 0, I basically don't need to shift my signal. So as the last step, I will multiply and add to get the summation of x of k multiplied by h of negative k. Let's do it together. All right, so I have y of 0 equals to sigma x of k, h of negative k, running from k equal to negative infinity to plus infinity. So I have the graph of x of k and h of k. I only need to draw the graph of h of minus k and multiply x of k and h of minus k point by point. So this is h of negative k, and it's going to be the flipped version of h of k. So 0, -1, and -2. That's my graph. So I need to multiply the samples of x and h of negative k point by point. So for k equal to -2, I have 1 for h of negative k, and I have 0 for x of k. So y of 0 is going to be equal to, for x at n equal to -2 is equal to 0, h of negative k at k equal to -2 is equal to 1, and so this is 1. So I'm going to multiply it by 1, plus, I'm ready for the second one. At k equal to -1, h of negative k is 1. This is 0, so I'm going to have plus 0 multiplied by 1. 0 is for x of k at k equal to -2. Then plus, I'm ready to check the values of these two signals for k equal to 0. So this is equal to, at k equal to 0, h of negative k is 1, and at k equal to 0, x of k is equal to 1 as well. So I'm going to write it as plus 1 multiplied by 1, plus, for k equal to 1, x of k is 2, and h of negative k is 0, plus for k equal to 2, x of k is 1, but h of negative k at k equal to 2 is equal to 0, so I'm going to write 0, plus for k equal to 3, x of k is 2 multiplied by 0. So if I add all of these, I'm going to end up with 1 for the value of y of n at n equal to 0. So y of 0 is equal to 1. I'm ready to move on and calculate y of n for other values of n. All right, let's take a look at calculating y of 1 at n equal to 1. That's going to be equal to sigma x of k, h of negative k plus 1, k from negative infinity to plus infinity. So I want to do this, calculate this summation graphically. I have the graph of x of k. I have the graph of h of k. I only need to draw the graph of h of minus k plus 1. In the first example, you saw how to do this one. So I need to flip h of k and then shift it by 1 point to the right. I'm going to flip it and shift it by 1 point, so that's going to give me -1, 0, 1. The amplitude is 1, and this is h of negative k plus 1 as a function of k. All right, so I'm ready to multiply x of k and h of negative k plus 1, these two signals point by point for all k values. So y of 1 is going to be equal to, for k equal to -1, I have 0 from x, and I have 1 from this new signal, h of minus k plus 1. For k equal to 0, I have 1 from x of k. This is the signal that I'm talking about. And I have this one I have that sample from x of k and this sample from h of negative k plus 1. So 1 multiplied by 1, plus For k equal to 1, I have 2 from x of k, and I have 1 from the shifted h of k. All right, so that's that. Plus, for k equal to 2, I have 1 from x of k, and I have 0 from h of negative k plus 1. Plus, for k equal to 3, I have 2 from x, and then I have 0 from the other signal. All right, the rest are 0. For all other k values, both x and h are 0. So other than k equal to negative 1, I didn't write this one. Did I write it? Yeah, I included this one. This is the sample of x of k for k equal to negative 1, and the sample of h minus k plus 1 for k equal to negative 1. So I included everything. So the rest of these, the rest of the components in this summation is equal to 0. That's going to be equal to 3. So y of n at n equal to 1 is equal to 3. All right. Moving on, I want to find y of 2. That's going to be equal to sum of x of k, h of minus k plus 2 for k equals to negative infinity to plus infinity. So I have x of k. I'm going to plot h of minus k plus 2, h of minus k plus 2. To do that, I need to flip h of k and then shift it by 2 points to the right. So that's going to end up with signal that looks like this: 0, 1, and 2. Amplitude is 1. So this summation is going to look like this: 1 multiplied by 1 plus 2 multiplied by 1 plus 1 multiplied by 1 plus 2 multiplied by 0. That's equal to all of the other components in this summation are equal to 0. So 2 plus 2, 4 plus 1 equals to 5. 1, 3, 4. It's equal to 4. All right. So y of n at n equal to 2 is equal to 4. All right. Moving on, I want to find y of n at n equal to 3. That's going to be equal to sigma x of k, h of n minus k for k equals to negative infinity to plus infinity, and n should be equal to 3 here. So I need to plot h of 3 minus k, or h of minus k plus 3. So I have this one, and then I'm going to flip h of k and then shift it by 3 points to the right. So that's going to be 2 and then 3. All the amplitudes are equal to 1, and the rest is equal to 0. So if you do that, y of 3 is going to be equal to, I have this sample which I need to multiply by this, the amplitude of those two signals at k equal to 1. So it's 2 multiplied by 1 plus 1 multiplied by 1 plus 2 multiplied by 1. That's going to be equal to 5. So I got the value of y of n at n equal to 3, and that is equal to 5. You can continue calculating the values of the samples of y of n the same way that we did for n equal to 0, 1, 2, and 3. And if you do that, you're going to end up with y of 4, which is going to be equal to 3, y of 5 is going to be equal to 2, and y of 6 is going to be equal to 0. So I also plotted the graph of y of n. This is y of n as a function of n for different values of n, and I plotted it with the stem function. All right. Now that you saw how to graphically compute the convolution, let's look at another example, which we are not going to use the graphical method, but we are going to use the equation of convolution to find the convolution of x of n and h of n. So x of n is alpha to the power of n u of n, and h of n is beta to the power of n u of n, and this absolute value of beta is less than 1 and greater than 0. Absolute value of alpha is between 0 and 1, and alpha and beta are not equal. So let's take a look. I'm going to write the equation of convolution is equal to x of n convolved with h of n, which is equal to sigma x of k, h of n minus k, k from negative infinity to plus infinity. All right, so then I'm going to write this one as sigma. If I have x of n and I want to find x of k, I'm going to write alpha to the power of k u of k. I'm going to replace n with k whenever I see n in the equation of x of n, in the expression of x of n. So it's running from negative infinity to plus infinity, multiplied by, I have h of n and I want to find h of n minus k. Whenever I see n, I'm going to change it to h of n minus k in the expression of h of n. So that's going to give me beta to the power of n minus k multiplied by u of n minus k. Okay, I can simplify this summation by noting that this u of k in here is 1 when k is equal to 0 and positive for all positive values of k, and equals to 0 for negative values of k. So that's going to give me sigma alpha to the power of k. Instead of u of k, I'm going to write 1, and then I'm going to change the limits to 0 to plus infinity, and that's going to that I'm going to write b to the power of n minus k as b to the power of n multiplied by b to the power of negative k, u of n minus k. All right, so I need to replace u of n minus k with something. It's either 1 or 0 depending on the choice of n. So let's take a look at how I can take care of this one. So I'm going to write u of n minus k. I'm going to treat it as the transformed unit step function, and I'm going to say that this is equal to 1 when the argument of this step function is greater than or equal to 0, and it's 0 when n minus k is less than 0. So then that's going to be equal to 1 when n is greater than or equal to k, or k values are less than n, and then it's 0 when n is less than k. All right. In this summation, I have here in this summation, my sum runs from k equal to 0 to plus infinity. So the k values are positive. So by just looking at this expression, I know that u of n minus k is 1 for n values greater than or equal to k. Now that in my expression, in my summation, k is already a positive or a number or a number already is equal to 0 or a positive number, I can say that I can replace u of n minus k with 1, providing that n is greater than or equal to 0 and k is less than or equal to n. So I'm going to put a note in here. For n greater than or equal to 0, I can write this one as k equals to 0 to n alpha to the power of k multiplied by 1 multiplied by beta to the power of n multiplied by beta to the power of k multiplied by 1. Right. For n less than 0, then this summation is equal to 0 because u of n minus k is 0. So you're multiplying everything by 0. All right. So at this point, I have for n positive or equal to 0, y of n is equal to sigma. Let me rewrite it. Alpha to the power of k, beta to the power of n, beta to the power of negative k, and k from 0 to n. Beta to the power of n doesn't have any dependence on k, so I can take it out. Beta to the power of k, sigma alpha over beta to the power of k, k equals to 0 to n. You can calculate the value of this summation using the geometric series that you have seen in your lectures. So I'm going to write this one. I'm going to replace it with its final value. The final value for this summation is beta to the power of n plus 1 minus alpha to the power of n plus 1 divided by beta minus alpha. All right, so this is for n positive or 0. For n less than 0, y of n is equal to 0. Okay, I can simplify this expression and write y of n equals to beta to the power of n plus 1 minus alpha to the power of n plus 1 divided by beta minus alpha, this whole thing multiplied by u of n. So this multiplying this expression by u of n tells me that if n is negative number, is a negative number, u of n is 0. So this expression is only non-zero for positive values of n. All right, let's take a look at some of the important properties for convolution. The first one is commutative property. It says for any signal x of t, for any two signals x of t and h of t, x of t convolved with h of t is equal to h of t convolved with x of t. And that means you can change the order of convolution. And for the case of discrete time signals, for two signals x of n and h of n, the answer of x of n convolved with h of n is the same as h of n convolved with x of n. If, in terms of the systems, the properties of the systems, if h of t is the impulse response of an LTI system and x of t is the input signal to that system, the output is going to be similar to the case that you apply h of t as the input signal to an LTI system whose impulse response is equal to x of t. Proof, I provided the proof for discrete time case. So I wrote the convolution equation, discrete time convolution equation in here. You had this before. And then we can do a change of variables. I can change n minus k to L. So whenever I see n minus k, I'm going to replace it with L. I see it in here. So this is going to be changed to L, as you can see in here. And then k is going to be equal to n minus 1. If n minus k is equal to L, then k is the same as n minus L. So I replace it in here. I replace k with n minus L in here. And then instead of running the summation for k from negative infinity to plus infinity, I'm running it for L from negative infinity to plus infinity. So this summation is the answer for h of n convolved with x of n. Basically here I shifted, flipped and shifted x of n instead of h of n. For the case of continuous time convolution, this proof is similar. So you can do a change of variable to show that, to prove the commutative property of convolution. Okay. The second property is associative property, which says for any three signals x of n, h1 of n, and h2 of n, if you convolve x and h1 of n first and then convolve the result with h2 of n, you're going to get the same answer as if you convolve x of n with the answer for convolution of h1 and h2. Or similarly, for the continuous time case, you can convolve x and h1 first, then convolve the answer with h2. The result is going to be similar if you convolve x with the answer for convolution of h1 and h2. It shows that when you have two systems that are connected in series, h1 of n, h2 of n, and the input is x of n, the output is y of n, you can treat it as convolution of x of n and h1 of n first, and then that's going to be input to the second LTI system. Then the output is going to be equal to x of n convolved with h of n, the whole thing convolved with h2 of n. Or you can the associative property says that I can find the answer for this one as if I convolve x of n with a system whose impulse response is calculated with h1 of n convolved with h2 of n. So you're going to get the same answer at the output. The last property of convolution is distributive property, which says for any three signals x of n, h1 of n, and h2 of n, x of n convolved with h1 plus h2 is going to be equal to x of n convolved with h1 plus x of n convolved with h2 of n. The result is similar for the case of a continuous time convolution. In terms of the systems, it means if you apply x of n to two systems that are in parallel with each other, h1 of n is in parallel with h2 of n, then the answer from these two systems are going to add up to make y of n. So if you apply x of n to these two systems that are in parallel, the answer is going to be similar to the case that you apply x of n to another LTI system whose impulse response is h1 of n plus h2 of n. The same goes for the case of continuous time signals and continuous time systems. Right. Thank you for watching.